Welcome back, Algebra 2. We're in Lesson 127. We're still on geometry, and this time we're going to talk about planes. Geometric figures that can be drawn in a flat surface with 2 dimensions are considered to be planar, and that should be an A right there, sorry. Planar figures, and the study of these figures is called plane geometry. The study of 3-dimensional figures is called solid geometry, and those figures occupy what we call space, which is 3 dimensions. We think of a plane as a flat surface that has no thickness and that extends without bounds. So imagine like if this continued in all directions continuously, right? It's a slice of reality on a thin sheet. That would be what we consider a plane. 3 points that are not collinear determine a plane. Collinear means all in the same line. So here, let me change colors. We have point B and point C, which are linear. They're on the same line. But then point G, which is not in that same line. Those 3 points create what's called a plane. And here we've labeled that plane P. Planes are labeled with lowercase letters. Points are labeled with capital letters, okay? Now, when we have 2 planes that intersect, the angle made by those 2 intersecting planes is called a dihedral angle. And that would be this right here in the center, this little angle here from this plane and this plane intersecting. Let me change color so you can see that. This angle here from the intersection of these 2 planes, this is a dihedral angle right there. If a line intersects a plane and the plane does not contain that line, so we have line EH here, then the line intersects the plane at only one point, and here we have that denoted as point F, where line EH intersects plane P, okay? Skew lines are lines in space that are not parallel and do not intersect. They don't have anything to do with each other. They're skew lines. That's their only relationship. Now, if a line is perpendicular to each of 2 intersecting lines at the point of intersection, boom, boom, the line is perpendicular to all lines in a plane that passes through that point of intersection. So every other line in this plane that passes through point A would be perpendicular to line L. Okay? All right. So we've gone over all of that stuff fairly well. Let's do a practice problem. Practice 127.1. Here we are given that PF is perpendicular to M. So this is perpendicular to M. GH, which is this line here. Am I drawing that right? Oh, I'm sorry. I wrote that incorrectly. It's not GH. It should be GF. I'm fixing to say there's not a line right there. So line segment GF is congruent to line segment FH. So these have the same length right there. We need to prove that line segment GP is congruent to line segment HP. So what we're going to do is we are going to do that through the property of looking at these as 2 right triangles, because if this is a right triangle, if this is perpendicular to M and GFH are a part of plane M, then these lines are perpendicular to PF also, because the plane is. All right, so then that means we have 2 right triangles. And if GF is congruent to FH, and we know PF is the other side, then we have side angle side that makes those 2 congruent. So we can write that out here. Given this, and here's how you do a proof. We're gonna move this down here. Actually, no, we're not. We're just gonna start at the beginning. All right, so we would say PF is perpendicular to M, and that's a given statement. And then we would say the line segment GF is congruent to the line segment FH. And that's a given statement as well. Then we would say, since PF is perpendicular to plane M, given, and it is perpendicular to, that means that PF is perpendicular to line segment GF and FH. All right, and so then we would say, because of that, so angles GFP and HFP are right angles. So angles, the measure of angle GFP and the measure of angle HFP equal 90 degrees, not percent, degrees. Right? So we are given the bases of the triangles, GF and FH, and they have equal lengths. So we see that PF is the side of both triangles. Thus, triangle GFP is congruent to triangle HFP. And that is by side angle side. And we have given our side angle side here. Therefore, line segment GP is congruent to line segment HP because congruent parts of congruent triangles are congruent. All right, let's look at the next one. 127.2. Given BC, D, and E are in plane K, line segment AB is perpendicular to plane K, line segment BE is a perpendicular bisector of line segment CD. We see that here. BE, perpendicular bisector of CD, and just by saying it's a bisector, we know it cuts it exactly in half. We need to prove that ADC is an isosceles triangle. Right? So, triangles BDE and BCE in the base are congruent by SAS. So we can say triangles BDE and is congruent to triangle BCE, and that's by side angle side. Okay, DE and EC have equal lengths. So we can put that little tick mark right there. Those are equal. The angles at E are both right angles right here. These are both right angles because that is a perpendicular bisector. BE is a perpendicular bisector of CD. So these are right angles. That's part of the given. Okay. So that means that BC and BD are congruent. So therefore, line segment BC is congruent to line segment BD. So these two are congruent as well. Right? And that is by congruent parts of congruent triangles are congruent. We can also show that the triangles ABD and ABC are congruent by side angle side. So triangle ABD is congruent to triangle ABC, and that's going to be by side angle side because we have side, the same angle, they're right angles because they're perpendicular to the plane, side angle, side angle, side, side angle, and this is the same side for both of these triangles. So side 90-degree angle, side, side, 90-degree angle, side, right? Side angle, side. Where are we? Okay, so that means that the angles at B are right angles and BA is the side of both triangles, which we know, which we just pointed out. So therefore, by, we can say that line segment AD is congruent to line segment AC. That means this one is congruent to this one. So it'll be 1, 2, 3, 4, 1, 2, 3, 4. Those are the same. And that's called from congruent parts of congruent triangles are congruent. Okay. So because this triangle is congruent to this triangle, this side is congruent to this side because they are congruent triangles. So if this side angle side proves that this triangle ABD is congruent to ABC, then that means the hypotenuse of both of these right triangles have to be the same as well. And that's called congruent parts of congruent triangles are congruent. So therefore, because BCD is a isosceles triangle, ADC is an isosceles triangle. So I can say A triangle ADC is isosceles by CPCTC. Alrighty, that's all we have for lesson 127. I know these proofs are require a little outside of the box logic and a little bit of thinking in regards to the next step. Like, what is the next step? How do I know which step would be the next step? Just look at it and find the next thing that makes sense, the next step that you can prove. You start with what you have and you look for the next thing that you can show is congruent to something else because of what you already know. And you move on to the next step and the next step and the next step until you get to the statement that you need to prove. Right? You just work your way around to it, proving each thing is congruent until you get there. Okay? All right. So never fear, when we have a test on these things, it will not be, stuff out of thin air. I'll give you the reference materials that you need. Then that's all I have for lesson 127. I will see you in lesson 128. We have 2 more lessons, 128 and 129, and we are done. I know y'all are so excited. I'm excited to see how well you do. I know that y'all are going to do awesome. Ta-ta for now.